Hi, I'm Mark Perry with Colorado Dam Safety. Welcome back to our tutorial on our new hydrology guidelines entitled Guidelines for Hydrological Modeling and Flood Analysis. This tutorial covers Section 3, an overview of our new CSU SMA modeling method. And we also cover a little bit of Section 2 and background to how we got to this modeling method. You can also look back at our previous tutorials. There's one on sections 1 and 2, which really focused on introduction to our new methods and comparing new methods with old dam safety hydrology modeling methods. And the big difference being our new use of observed flood data for model checking and calibration. The other tutorial we have is previous that you should look at previous to this is an overview of the state and Colorado Dam Safety's methods for hydrological evaluation of existing dams and for hydrology inflow design floods for design of new dams and modifications. So before you go into a modeling study, please understand why you're doing it, whether it's for evaluation of an existing dam, which we use hydrologic risk analysis, or whether it's for new design, for which we use an inflow design flood study. Okay, these are the new guidelines, and the dates may change. We will update them on our website if updates are made. And let's jump to our website and I'll show you where to find them. Okay, here we are at our Colorado Division of Water Resources Dam Safety webpage, and just show you where the hydrology guidelines live. So if you scroll down the page, first of all, you'll see under important links the hydrology guideline tutorial videos, which if you're watching this video, you've probably found that already. If not, that's where they all live. And then to get the actual guidelines document, you drop down this gray bar, guidance documents, formal directives, and currently at the top of the list, and they're listed as draft. They will be finalized hopefully by the end of August here, but regardless whether draft or final, you will find them here in our list of guidelines. Draft guidelines for hydrological modeling, flood analysis, and you can open those and download them. Okay, yeah, so let's first jump back to section 2 of the guidelines and talk about a little bit of the background of how we got to these new modeling methods. So our general experience at Colorado Dam Safety was that dam safety hydrology design floods were much larger than observed and paleo floods, at least in the mountains above 7,500 feet and on the west slope. So a couple years, 4 to 5 years ago, we had the opportunity to test out a new proof of concept hydrology model that would try to more accurately model floods in a mountain basin. So this was a front range mountain basin above 7,500 feet, about a 92 square mile basin. And this was a big site-specific study, so we had lots of stream gauge data, good reservoir records for the dam being analyzed, and then importantly, we had rainfall data and flood records from the September 2013 floods. So what did we do for our proof of concept study? Well, first of all, talk about the old hydrology methods. So generally, our old hydrology methods generally relied on infiltration, excess, loss or runoff methods. So modeled runoff as quick flow. But there's a lot of research that suggests that quick flow does not occur in mountain basins. That's because for a lot of reasons, but coarse grained soils, fractured bedrock, large pluvial deposits, forested, heavy vegetation, forested basins. So what we did in our proof of concept model was we developed a method that would allow much higher infiltration and loss rates, but at the same time, then it accounted for percent soil saturation and allowed saturation excess runoff, and then it allowed interflow or subsurface flow back to the streams. We also, previous methods also modeled quick flow by pretty severe or quick flashy unit hydrographs like the Bureau of Reclamation, flood hydrology manuals, Rocky Mountain thunderstorm unit hydrograph. So instead, for this proof of concept model, we used Clark unit hydrograph, which allows parameters to be varied, and we used a slower response that's probably more indicative of interflow or some kind of a slow muted runoff that's not quick flow. So here we see results at a site at a stream gauge near about 8,000 feet. It's on South Boulder Creek, and the graph here shows this September. Our model is September 2013 flood event at that location, and what we show here is the actual observed flood, the gauge data in dashed line, and then our proof of concept model, which again allowed much higher infiltration rates, did soil moisture accounting and allowed saturation excess runoff. And then in comparison, so our proof of concept model is the bold hydrograph. And for comparison, we looked at a traditional dam safety hydrology model, which used typical low infiltration rates and infiltration excess runoff. What you can see is our new model with high infiltration rates, subsurface flow, etc., was able to reproduce the hydrograph in the mountains very well. The old approach to dam safety did not produce too much volume and way too high peaks, too flashy flow, basically producing quick flow where most likely losses were very high and quick flow did not happen. Okay, just briefly then, here's results from our study at another site. This is lower elevation, about 6,000 feet, so actually in the Front Range foothills on South Boulder Creek. But here the point to make briefly is that there was a delayed peak in the observed September 2013 flood that our model was able to reproduce, but the traditional dam safety model was not able to reproduce. And why is that? Because the traditional model used low infiltration rates and a flashy quick flow unit hydrograph, so it produced the peak and a way too big of a peak at the peak rainfall intensity, whereas our model allows higher infiltration rates. More of that heavy rainfall was able to infiltrate, but then by the soil moisture accounting and subsurface flow, the peak actually occurred about 24 hours later, and that's what our model showed in the bold line, and in fact that's what the observed flood record, the stream gauge data at this site showed. And there was also an indirect peak. It's a little hard to see, but this triangle here, an indirect peak flow measurement made afterward to try to confirm that flood peak, verify the stream gauge data, and our model agrees well with that magnitude of the peak flow. So again, the traditional dam safety model, even at this lower elevation site, significantly overestimated peak flow from September 2013 floods and got the timing wrong. Our new proof of concept method did a good job on the timing and the magnitude of the flood peak here. Okay, now let's look at some tabulated results. These upper rows are just a summary of what you've already seen from the September 2013 event at the Pine Cliff site and then at El Dorado Springs. So again, just looking at it in numbers, our Colorado Dam Safety Model did a much better job, about 5% under for the observed peak flood compared to traditional dam safety hydrology model, which was way over. And same for volume, whereas at El Dorado Springs, we were about within 9% of the observed volume versus 30% over estimate from the traditional dam safety model. But let's jump. What I want to show you here is then extrapolating to using our model for the PMF modeling and then a comparison to observed paleo flood record. So for the PMF model, our Colorado Dam safety model, which arguably did a much better job reproducing the observed September 2013 flood, came up with a PMF peak flow of 16,000 CFS at Gross Dam. The traditional dam safety hydrology model produced a PMF peak flow of 40,000 CFS. So there we're less than half. Now, the subnote 1, this was again a site-specific PMP and PMF hydrology study. So PMP, this is using site-specific PMP. This study was done prior to our Colorado, New Mexico Regional Extreme Precipitation Study, or REPS, but it was done in a very similar manner. So this was using site-specific PMP. Now, if we go back to HMR 55A PMP and run the traditional dam safety hydrology model, the previous PMF for Gross Dam was about 90,000 CFS. So by using site-specific PMP, which we now have with REPS, we go down by to less than half, to about 40,000, and then by using our new hydrology proof of concept model, we went down to less than half again. So now let's compare it to the which one is right. Let's compare it to the observed flood record to try to get some kind of check of reasonableness. So we have good stream gauge data there. Bulletin 17C analysis, the 500-year peak flow estimate at El Dorado Springs, which is even a larger, lower elevation and larger drainage area size, was about 5,000 CFS. So our PMF estimate using our proof of concept hydrology model and site-specific PMP rainfall is still over 3 times that. Okay, pretty good. Also, we had good paleo flood estimates in this region. So we have a reclamation paleo flood estimate at Olympus Dam, which is a larger drainage area, but about the same elevation and very similar basin physiography. Their paleo flood estimate was 3,000 to 5,000 CFS over an estimated period of 3,000 to 5,000 years. So again, our proof of concept model PMF peak flow is there about 3 to 5 times that paleo flood estimate at Olympus Dam, and likewise the reclamation had done a recent paleo flood study at Button Rock Dam, somewhat larger drainage area a little larger drainage area than Gross Dam, but they had a paleo peak flood estimate of about 7,300 to about 10,000 CFS over 6,500-ish years, and our proof of concept model with site-specific PMP rainfall PMF is still 1.5 to over 2 times that paleo flood estimate. So the point being that there is working backwards from the old HMR 55A PMP and traditional dam safety hydrology models, 90,000 CFS PMF, to the traditional dam safety hydrology model with site-specific PMP, 40,000 CFS, to the site-specific PMP and our proof of concept mountain hydrology model, 16,000. There was definitely potentially big decreases in big benefits of developing more accurate rainfall and runoff methods, at least for this basin. Okay, so all that was in the way of background how we got to our current CSU SMA modeling method, which is the basis of the new hydrology guidelines. So let's jump to that. We saw these good, encouraging results from our proof of concept model and our site specific study. But that model was very cumbersome and it was in no way kind of reproducible, and it was not reproducible for ungauged basins. We had a lot of gauge data to calibrate it by. So we took that approach to Colorado State University and we started a study with them to develop a um, a more usable model hydrology method that would incorporate the same aspects. So those are higher infiltration rates, soil moisture accounting, subsurface flow, and then more variable or the ability to do slower surface runoff response by unit hydrographs. So this was this started about 4 years ago. We went through several graduate students, 2 phases of study, and two ended up in 2 master's theses, 2 published papers. The first phase of the study was a calibration study in about five Front Range basins and 3 historical extreme floods. And then the second, they developed a modeling method from that. The second phase of the study then was a verification phase and development of parameter estimation methods for ungauged basins. So they developed estimation methods, then applied those to 3 different basins and I believe 5 different extreme floods in the San Juan Mountains. So this is a schematic of what they came up with. We said that we told CSU we wanted the modeling method to be readily accessible, preferably using HEC-HMS since it's a free software and general use by consulting engineers. And they used the HEC-HMS soil moisture accounting method. This is the schematic. So it starts, the subbasin model in HEC-HMS starts with a canopy storage method for vegetative interception. Any rainfall that exceeds that volume goes to the soil through fall, when through fall exceeds infiltration rate, or up into the infiltration rate, it infiltrates into the soil. And when it exceeds infiltration rate, it goes to surface runoff. For the losses and subsurface, they use this HEC-HMS soil moisture accounting method, and that allows soil volume to be accounted for. The soil storage is filled up, and as it's filled up, infiltration rate decreases from its maximum infiltration rate at 0 soil storage to 0 infiltration at soil saturation. So this is the big difference from previous methods. We can allow a higher infiltration rate, more realistic at the front end, but then account for soil moisture, soil saturation by the soil moisture accounting when infiltration would stop and produce saturation excess runoff. Now, from that soil store, we can also get water percolating into a first groundwater level, groundwater 1 storage, which would mimic fractured bedrock and interflow. That water can come out of soil storage and flow as it interflows subsurface flow by linear reservoir base flow in HEC-HMS and return to the stream, or it can percolate out into deep groundwater, the groundwater 2 level, which is a loss to the system. So let's take a look real quickly. We'll get into a lot more detail in future tutorials, but let's take a look real quickly at HEC-HMS and see what it looks like. Okay, here we are in HEC-HMS. This is HMS version 4.10. CSU's research was done using HMS 4.7. So the guidelines are kind of written towards that. But as everyone familiar with HMS knows, HEC changes it a lot, issues a lot of updates, and usually the updates are pretty minor. So far, have not seen any major changes that would affect our CSU SMA modeling method. But I'll just do a real quick overview of the CSU SMA method model setup in HMS 4.10. So the overview is this of a subbasin element, and then you see which methods are used in the CSU SMA method. Canopy, simple canopy method, no snow, no surface. A loss method is the soil moisture accounting method. The transform for quick flow or surface water, conceptually surface water runoff, even though that may be shallow, subsurface flow or something. But that's the transform is the Clark unit hydrograph method. And then for that flow, inner flow out of the groundwater one level, in the SMA method, we have linear reservoir base flow. Okay, so just clicking through those real quick. In the method, we give the parameter. CSU gives parameters, values, recommendation guidelines, I guess, for the canopy. And you'll set these different properties here, and then for our loss, the soil moisture accounting method. Now, the soil moisture accounting method has a lot of advantages, which I already talked about, and what we've seen in the producing different types of runoff and the kind of delays in runoff that we've seen in Colorado in extreme floods. But the downside of it is obviously that it has a bunch of parameters. So that was a big part of phase 2 of CSU studies, coming up with parameter estimation methods for us, especially for ungauged basins, which is a lot of our dams. So for that, we've developed, or they developed, and we kind of honed an ARC toolbox tool that estimates these parameters for you. And as I said in the future tutorial, really we think you'll find, once you've done it a few times and get through the learning curve, we think you'll find it pretty easy. It's an automated, using digital data sets, and pretty automated and reproducible method in comparison to a lot of past model parameter estimation methods that tended to be subjective and more of an art. So even though there are more parameters here, in the end, we think the new method's probably easier. All right, so then transform any surface runoff we generate. The guidelines use the CSU SMA method uses Clark unit hydrograph. It's a well-established method, generally acceptable, as the guidelines talk about. It's especially when we use our checks and calibration against observed floods. Unit hydrograph approach is generally, we found, in this research study, calibrating the floods, verifying floods, the unit hydrograph method is generally acceptable, adequate for reproducing, estimating floods. There may be case by case for more detailed levels of analysis, like a 2D model, like RES 2D for surface water or surface runoff transformation, or other softwares for developed areas, or if there's a lot of complex drainage system. All right, and then base flow. Lastly, that's again going to be that return groundwater and produce inner flow, and that comes out of the groundwater one level in the SMA method, and the CSU SMA tool gives parameter estimates for that as well. Okay, just real quickly, I want to show a table of results from CSU's Phase 1 Mountain Hydrology Study research. And we've probably already made this point, but I want to hammer home that they found that the SMA method and the approach to allow soil moisture accounting, saturated excess runoff, delayed runoff, and subsurface flow was necessary and sufficient to reproduce observed extreme floods in Colorado's mountains. But the question, I think that historically the assumption with dam safety hydrology is, okay, I mean, that's fine for observed floods, more frequent types like 100-year, 500-year average recurrence interval. But the floods of concern of dam safety are so extreme that basically nothing else matters because everything's just going to run off. I'm saying that was, I think, the previous assumption. Things like assumptions like everything's saturated, no initial abstractions, things like that, minimum infiltration losses. But what happened is, so CSU then, after they had calibrated their model, the phase 1 model to these 5 basins and 3 extreme storms, then they took our REPS design rainfalls and they ran those on the calibrated basins. And the what's shown here is each basin, and then the second column here, the REPS storm types. So the 1 in 1,000 through 1 in 10 million AEP precip frequency storms from our REPS Met portal, and then REPS PMP. And the bottom line is what they found on in this last column. They described, or they listed which runoff mechanism was controlling the runoff for that scenario. And what they found, bottom line, is that varies. And so it varies, the runoff mechanism, either SE, saturation excess, i.e. Infiltration excess, so, traditional Horton runoff. The case of both is obvious, and then none is actually subsurface flow. So there we even have an instance of subsurface flow dominating in one instance. But what they showed is that the controlling runoff mechanism varies by basin, your site-specific basin, by storm magnitude, and then also by storm type. So I guess I didn't mention that. This third column is REP storm type. So, if you're familiar with REPs, you know that within we have a 1,000-year AEP, but that's divided into storm types. So you have a 2-hour intense thunderstorm, 6-hour mesoscale with embedded convection, 48-hour mid-latitude cyclone. So different storm types, same with PMP. And so the runoff mechanism is going to vary by basin, by storm magnitude, and by duration, controlling storm type. So again, even at the extreme storms of interest in dam safety, CSU showed that this new runoff modeling method is the elements of that new runoff modeling method are necessary and an advancement, really. Okay, to start to wrap up this tutorial, I want to go through some actual results when we've left once the CSU research was wrapped up and we started applying the new methods, some actual results, and then comparing them to talking about observed floods and paleo floods in Colorado, and how do the modeling results compare to those. So here's in the guidelines include regional peak flow envelope curves. And so this is a plot of observed peak flows and paleo peak flows versus drainage area log scale. And we've divided these up into regions. This is for the mountains, the central mountains above 7,500 feet. And all the dots below here are observed floods, some of the most extreme from indirect measurements. And paleo floods are the triangles. The blues tend to be more gauged, the gauge data. And then we've enveloped that. Our envelope is the red line. We're going to ignore the green line for now. It's an old envelope, and there's a reason that it is up there, and we don't. A reason why we don't use it, but for now, just let's ignore that. Now, what I want to show you is these are results, actual. Well, and maybe just show quickly that the dotted lines here exclude dam failure. So it's pretty obvious when these flows, these regional envelopes tend to behave pretty well, and when you see something like a dam break, it's kind of obvious that was not natural flow. So we don't we obviously don't envelope those, but I just wanted to call those out to make that point. So what we show here is results from 4 basins, and these are in northwest Colorado in the Yampa River Basin, comparing old hydrology methods versus the new hydrology methods. So in old HMR rainfall, old traditional hydrology modeling, and then new methods with REPS rainfall and the new hydrology. And these are pretty much uncalibrated runs of the CSU REPS and their CSU SMA hydrology method. And when we plot those up, you can see that they compare really well at 4 different basins, 4 different basin sizes, compare really well with our regional peak flow envelope, so maximum observed floods in this region. Whereas the old hydrology methods, HMR and old traditional hydrology, the old results not so much. They're way above the observed envelope, and remember, we're talking log scale here, so these are pretty big differences of going, say, in this case at let's say a case at 987, about 7 square miles, going from 4,000 up to probably something closer, the old method, about 20,000 CFS for these are PMF, modeled PMF peak flows. Okay, so again, we're relying on, when we see differences in all these methods, which is right, and what these new guidelines incorporate is use of the observed flood record. So we propose that we know which is right by comparison to the wealth of observed floods, regional observed floods in Colorado. Okay, and then to further that, what the new modeling, what the REPS rainfall and new hydrology modeling is showing us is that those traditional PMFs and modeled floods may come down a lot, and there's a lot of regional variation, like I showed in the results from our site-specific study and proof of concept model. But there's good reason for that, and there is probably a 30-year research and data effort to show those differences. And like I've said before, it involved USGS and really the Colorado State climatologist and Bureau of Reclamation. A lot of people have put together these data and paleo studies. So here's an example from Bob Jarrett and Ed Tomlinson paper of study of a really detailed study of flooding, paleo floods and historic floods in northwest Colorado, and to illustrate a point, they plotted similar plot to what I just showed, but here unit discharge versus elevation, and of course in metrics. This was a journal article, but the point, the point here is not so much the units, it's just the regional differences. So 3 main points here that we see is below. So, and the key thing is that Bob Jarrett's key hypothesis has been this 2,300 meters, which corresponds to about 7,500 feet, and that seems to be a limit to intense rain-driven flooding. that above that, Jarrett proposed that there's no paleo flood record or historic record of rain-driven flooding above that elevation. So what he showed is when he mapped out an envelope of historic and paleo floods below about 7,500 feet, first thing is eastern Colorado, east of the Continental Divide, floods are going to be much higher, order of magnitude higher than they are when you get above 7,500 feet. So going up in elevation towards the Continental Divide and then through the mountains, these floods, once you get above 7,500 feet, observed floods are much lower, like order of magnitude. Okay, and then the next difference is eastern Colorado versus western Colorado below that elevation. So comparing kind of the Front Range foothills and eastern plains with western Colorado. And again, even below 7,500 feet, you're going to see a large difference between eastern Colorado and western Colorado. And I think those are the points. Okay, and another way, another study that we can see these regional differences and observe floods was from Smith and Water Resources Research, 2018. And here they tried to look at the kind of skewness or extreme nature of some observed floods. And they took the USGS flood database, peak flow database, and calculated what they called an upper tail ratio, which is an observed flood peak flow divided by a 10-year flood frequency estimate at that same location. So kind of you can kind of imagine the farther, more highly skewed or farther out that observed flood was on the tail of the distribution, the bigger that ratio. So the red dots show ratios above 20, and then green 10 to 20 kind of medium, and then low 5 to 10 for that ratio of blue. And so what you can see is most of Colorado is, blue and green when they looked at those sites. But clearly there is a regional line here that goes along the Front Range foothills of the Rocky Mountains from New Mexico up through really Wyoming. And where we have some potential for and have observed some very extreme floods in terms of this upper tail ratio. So regionally, we do see big differences, and those are the guidelines will show that those are accounted for with our new REP study and this new modeling method. Whereas the big problem with the old HMR rainfalls and old traditional hydrology methods is they generally did not recognize these regional differences. And basically what we see is those previous studies took limited data where the flooding was mainly along the populated Front Range foothills and eastern plains, and they extrapolated or used that data across the entire state, and they did not represent the regional differences that we see from the observed flood record. Okay, as we wrap up this tutorial on the background and overview of our CSU SMA modeling method and the guidelines for hydrological modeling and flood analysis, I just want to catch a few miscellaneous items that are in the beginning of the guidelines. First of all, the table of contents. Let's just do a quick overview of that so you have kind of oriented to the future tutorials. Inside the front cover, there are flow charts that show an overview of our two different approaches to hydrology evaluation for Colorado dam safety. The first one shows risk-based hydrological evaluation for existing dams, and then the second flow chart shows the process for determining inflow design floods for any design project for new dams, modifications, enlargements. The guidelines then have the introduction, background, and overview, which we've already covered in these first tutorials. And I should mention these flowcharts 1 and 2 are covered in a separate tutorial that specifically discusses our two different approaches. There's risk-based approach hydrologic risk analysis versus inflow design flood studies. Okay, so then I have a tutorial in sections 1 and 2, this current tutorial, which basically covered 2 and 3. Then from here, we'll go through and do basically a separate tutorial for each. We'll go through the CSU SMA modeling method, data, the input data you need, how to get it, then how to determine subbasin properties, how to use the CSU SMA Python tool in our toolbox, ArcGIS, to estimate parameters, set up your model, what output you get, and what we want to see. And then lastly, the our incorporation of new flood data, of observed flood data for checking and building confidence, evaluating confidence in the modeling results, and then for calibration, if necessary. We have acknowledgments for the many people who, this is built on and who helped with these guidelines, and then references. So this document's meant to be very transparent. All references are listed, and we have a Google Drive link in the guidelines PDF that will provides most of these references at the ready, so you can find them easily. Appendices. We show example reporting requirements, the actual CSU SMA Python script, which you can get the actual script to modify it if you want. It's essentially open source. Reporting checklists to help the users go through these modeling process, and then the reasonableness checks process and report on them. And then in Appendix D, we have documented the subject matter expert review that these guidelines went through. Okay, and in red, this inset here shows that in red we mark reporting requirements in red with this paper scroll, and that's to help the user prepare the reports and documentation as you go through. So one of the goals of these new guidelines is not only to make the process easier, more reproducible, but to standardize our reporting requirements so that every hydrology report does not need to be a one-off. Okay. Next, we wanted to just miscellaneous items. We wanted to mention that we have other guidelines that support these hydrology. The current guidelines we're talking about are just for hydrological modeling and the use of the flood analysis, use of the observed flood record. But we have separate guidelines documents that are also on our website. One is for the use of our regional extreme precipitation study tools, and that will walk you through using the MET portal for precip frequency estimates, and the REPS PMP tool in ArcMap, a GIS toolbox for estimating site-specific PMP. And then in support of hydrologic risk analysis, we have our guidelines for hydrologic hazard analysis. So that's essentially what we call, that's our consequence analysis for flood failure modes. And this is how we do look at modeling flood, hydrologic breach analysis, and then consequence estimation using reclamation's consequence estimation method. And that's the end of this tutorial. I just want to say another kind of qualifier in the guidelines include several limitations and qualifiers, but a big kind of, I guess we'll call it a caveat, is that the approach here it does require expertise of the user, so the engineer or hydrologist. The first few sections of the modeling may seem overly prescriptive, stepwise, just putting together the data, the parameter and property estimation. It almost seems kind of, like I said, it's very automated and maybe just overly prescriptive. But then the real expertise comes in the evaluating observed floods, regional differences, looking at flood records, flood frequency analysis, the peak flow envelope curves. If you have records at a dam, frequency of spillway flooding, history of overtopping, maximum observed flows, maximum reservoir stages, seasonality, time of year floods, flood types that have historical flood types, and matching all of that up to make, and paleo floods, I should say, regional paleo floods, but putting all of that information together, hopefully multiple lines of information to make the case that the model is giving reasonable results for our dam safety floods, for hydrologic risk analysis and inflow design floods. So that's where the expertise really is, in building that case, making that case, and then also assigning a confidence rating to the model, to the modeling results. Okay, so that's it for this kind of background and overview. And now next, join us for section 4, where we'll get into the actual modeling method. Thank you.